Welcome to Splunk Talk. Boom, boom, boom.
Nice.
The Splunk podcast, that's all Splunk and no junk. This is season 2, episode 26. And we've got a special guest, Jerry Peng, is joining us in just a few moments. But before he gets here, how are you doing today?
I'm doing pretty good, man.
Yeah,
I am. I'm excited. I'm about to go on a road trip with family, like me and 3 kids and my wife in a minivan across the country, 20 states. This is starting to sound, when I say it all together like that, this is actually starting to sound worse and worse the more that I talk.
Is it fair to say someone is going to be driven crazy?
That is possible. That is possible.
What's the first song that gets played on the road trip?
I don't know, but I know the song that we were just singing a minute ago.
Black Eyed Peas?
Yeah, but I don't know if that's the song that we'll be playing first or not.
Well, I think we've just decided actually, it needs to be. Yeah,
I think that'll be the first one in the playlist. I mean,
yeah. You think at one point you're required to listen to On the Road again?
We probably will, because this is going to be a big road trip. I've never done one this long like this before. So
yeah, and it's weird. You're doing it all in a sedan.
Not a sedan. No, it's actually a minivan. So it's tall. It's a tall sedan. But anyway, I'm excited. We're going to be gone for like the month of June kind of thing. I'll be working from the road. We'll see how that goes.
Wow. I
will not be attempting to record a podcast, but I don't know. It could happen. I mean, we could talk about that.
Yeah.
What's up with you?
I am dialing in today. I don't know why we say that. No one dials anymore.
You're phoning it in.
It's like I'm phoning it in.
Low effort, you know.
Yeah. I'm phoning it in from my personal machine. What's that? What happened to my work laptop? I'm glad you asked. It was in a bag on a shelf. Mm-hmm. The bag also contained a smoothie in a enclosed container. Okay. I think we all see where this is going.
I am starting to understand what's going. I am a little confused as to why a beverage would be inside of a bag, generally, just on general principles.
Yeah, I like to live dangerously. Okay. Because it was, it was sealed closed. Mm-hmm. It was a bad call, I guess, to put it up high. What is that called in physics? Kinetic energy or something, potential energy.
Inevitability.
Yeah. So a little bit of smoothie on the laptop. And
did it boot up at all, or
what?
Did it boot up?
Boot it up. I had to do the Nintendo 64 or Nintendo cartridge thing on all the ports, clean them out with like Q-tips and rubbing alcohol and stuff. And some of those power ports and stuff could not get smoothie out. So there I am going with smoothie shooting back into my eyes as I do it. And I'm like, yeah, this is pretty much what I deserve for being that dumb.
Yeah. Well done.
Yeah.
Well done.
So then I took it to the repair shop, the local repair and shop. And in that moment, I drop it off and the guy goes, "So what's the password?" And I'm like, "Deer in headlights." And he's like, "I need to log in to validate." And I was like, "Yeah, I can't. I can't do that." Yeah. So I call up IT and I'm like, "Do we have a guest account I can enable?" And next thing you know, my phone's not working. It's not dialing out. The laptop can't get on the internet because my phone can't become a hotspot. Mm-hmm. I would imagine the place has Wi-Fi, but that's not the decision I made. And so here I am, IT, I got the phone on the neck, talking to IT, trying to figure out how to enable it, getting error messages on enabling the guest account while they're saying, well, what message does it say? So now I'm taking pictures with my phone and sending it through Slack on the phone. And mind you, I don't have a trackpad. So I'm doing this all keyboard commands and touch screen. Yeah. And was not able to get the guest account going. And I was like, really? I just wasted like an hour of commute time just to like walk home. And fortunately, I was able to use my technical wizardry, and I found a super secret account that I re-enabled. It was disabled. And that allowed me to do what I needed to. But it was a very funny moment. Speaking of funny moments, here comes Jerry.
Well, he's joining on audio now. I think he's joining on audio now. I see Jerry.
Hi,
there we go. Hey, Jerry, we were just catching up about how things have been, and we're really glad you're here because we got some really great feedback from some of our very passionate fans. Actually, I wish I had the name and email queued up, but I closed everything.
It was Roger in Seattle.
Roger in Seattle? Or is that just what we say for everything?
It was just the first thing that I thought of.
I believe we got a call from Sleepless in Seattle, and Sleepless said that they want these things to be more technical.
Yeah.
Jerry, do you think you can help us make this just a itty bitty bit more technical?
Sounds good to me. I'll do my best. And, thanks for having me, on board today.
Yeah. Yeah. Jerry, he hit me up a minute ago in Slack and he said, is there anything I need to do to prepare? Are there, common questions that you ask? And I didn't give him a thing. I did not give him a thing. So
you got nothing. You're cornered now.
No, well, the cool thing about what we do, though, I mean, the whole point here is that it is conversational. So don't you worry.
Yeah, just make sure it's all Splunk and no junk. And by that, I mean half of our conversations are about like movies and junk.
But we're going to get more technical in this one, we promised.
Yes. So Hal, I nominate you. Hal, I choose you. That's sort of a Pokemon reference. To introduce Jerry. Okay. Because you're more familiar with his work than I am. This is the first time Jerry and I have met.
What I'd rather do is have Jerry introduce himself. I mean, usually what we do, we start out, we say, so Jerry, welcome to the show. We are very happy to see you here. Why don't you just tell us a little bit about yourself? You can go back, not birth, but maybe age 4. No.
Well, and just to follow the pattern, now I nominated Hal. Hal nominated Jerry. Jerry, you have to nominate back to me to introduce you. Jerry, what's your origin story?
Your story. Yeah, we do
your orange story.
I am a developer by day and vigilante by night.
Wow, I did not expect that at all.
Or probably more developer at night nowadays. But
ironically, you were always wearing a face mask during your vigilante work, but now everyone's wearing one, so you really blend in.
Exactly. Yeah. So again, thanks for having me on board today, and to give kind of a background into my career. So in terms of my career, I've always kind of been in the area of distributed systems in the realm of computer science. From my undergrad days, I've done work with professors in that area of research, and more specifically at grad school, I got into a kind of a more specialized area of distributed system known as distributed stream processing. Mm-hmm. So from there, I done, a fair amount of research, written a couple of papers, went on to,
Are you a doctor?
I decided not to pursue a PhD because,
good, because I have this injury here. I was really going to ask you about.
No, please no.
Maybe I can write an app to, tell you the answer, but I will not be able to tell you the answer directly.
So in college, you started to specialize in distributed systems and then streams processing. And at what point did you kind of enter the workforce? Did we have the pleasure to be that first one, or did you have a series of spots before you hit Splunk? Were we?
Unfortunately, Splunk was not my first job.
It's all right.
one of the reasons I decided not to pursue a PhD is I had some opportunity to work at Yahoo to implement some of my research. So I took that opportunity to, first of all, make some money as a poor college student, as well as actually, make something practical out of my more or less theoretical, research. So
that's pretty incredible for someone to be like, hey, you wrote a paper on this thing. Now we want you to make it. That's awesome. What was the paper, or what's the gist of what you were hired for?
The abstract, please. No, don't.
Yeah. So the title is resource-aware scheduling and stream processing systems.
Okay. So
the gist is basically some more intelligent scheduling strategies that we can employ in distributed stream processing systems, so that we can get higher throughput and lower latency. So it was basically.
Let me ask.
Go ahead.
Sorry. Just to make this material as accessible as possible. We've talked about stream processing in other episodes, in other contexts, but I'd like to know what a not PhD describes stream processing as.
Sure. So think about stream processing as, just processing a continuous amount of data. Think about, perhaps a good example would be tweets, right? At any point in time, someone could go to Twitter and type in a tweet, submit it, and, it'd show up on the internet. Think about that as basically a continuous set of data, right? People are continually writing tweets. And what stream processing can allow you to do to say is, look, there are some bad folks out there, right? That's using dirty language or using whatever that's, that shouldn't be allowed on, Twitter. And we want to, selectively maybe filter some of that out, or selectively flag some of it. So, someone can make a decision on whether this questionable content should be, displayed or not, right? So that's a good kind of use of stream processing, where you basically get, a live stream of tweets, you feed it into a stream processing system, it applies some algorithms on that, right? It could just be a simple filter, it could be some enriching, it could be whatever logic that you really want to kind of apply to that, and then produce some sort of result. So you can kind of view that as, kind of a basic use case of stream processing system. There's many other use cases. And what I just said, I just realized should not be construed as a way for me to, censor people on Twitter or whatnot, but just as an example to say like what can be done with Twitter as an example data source.
So to pivot to a different example than social networks, I guess like if I'm like a commercial site, a commerce site, like an Amazon or something, or eBay, and I have transactions coming in, could anything be a stream of data?
Yes. To be honest, I would say probably most things are streams of data, right? What a stream of data usually means is data with a time dimension attached to it, right? Some sort of time dimension. And almost all data, I would say, more or less are created in that manner, right? You're basically creating, go ahead.
Yeah, I mean, is it fair to say that
here and ask, I'm sorry, go ahead, Rich.
Well, just like, I guess I never really thought through this until now, but like, is it fair to say like a stream of data is like almost like the stateless, like the UDP of data, like it's coming in. I mean, not that it's like lossful, or lossy, but like the data is like coming in, it's not at rest. Is that the difference? Like stream with the opposite of it would be like data at rest, like data stored on a disk for historical purposes.
Yes. So that's a popular term to be used in the stream and the stream processing kind of community is, data in motion versus data at rest, right? Data in motion is usually used as a term to classify, stream processing. Though kind of my point was like, in reality, everything originates, I would say, as a stream of data, right? Data is always produced or generated in a continuous fashion. It's only an artifact that people decided to, okay, we're going to just dump it all into, a file or storage to store it and then process it at a later time. But I would almost postulate that most data, if not all data, is actually always generated more or less in a stream fashion, as in it's continuous. It has a time, it has a time element, and it's, it's never ending, right? Just like, any sort of sensors, any sort of just like transactions that you mentioned, it's continuous, right? You don't really have any sort of endpoint per se, right?
Now I see Hal raised his hand. Hal, do you have a question, young man?
Please. Yeah, please. Yeah. Please. So I want to dive into how stream processing, why it became important. Before I do that, I want to just really quickly blow past, like, because I don't want to spend a lot of time on it, but I want to just kind of note that after Yahoo, you worked at Streamlio. Streamlio was acquired by Splunk. You did a lot of stuff with Flink and Pulsar and some other distributed systems. And I want to get back into some of that, but I want to just kind of quickly mention, because I know that Pulsar is super important to you, so I want to focus on that in a minute. But before I do that, why was it needed to focus on stream processing separately? Because I know what came before it was batch processing. What limitations were there that caused us to need to focus on a different way?
Anyone following mapping this at home, we just mapped from the word stream to its successor, processor and processing.
Thank you.
Yeah. You can lower your hand now, young man.
Okay.
That's a very good question, Hal. So I think originally why batch processing came to be is it was easier to reason about. I have a file, I'm going to do some sort of processing on that file, and then, I'm done, or I basically periodically, run my program to do some sort of, processing on some static file, and then, I'm done. So that's probably, the reason why, batch processing came first. And what people realized in that kind of model is, well, there's going to be some delay, right? And kind of when I can get results, right? Because I'm either, executing something, executing some sort of computation or processing periodically, or I'm basically dumping stream data, right? Live data into a file, I'm batching it together, right? And then, that data basically has waited in my file or storage for a while before I'm able to process it. So all of that time has, elapsed, right, before I can actually get a result. And people realize, well, we can get more opportunity, right? We can, if we're able to get results faster, we can take advantage of certain opportunities faster, and maybe that will be advantageous to us. So that's kind of where, stream processing comes in, is look, you don't need to no longer, wait a super long time before you get results, right? You don't need to dump it into a file and then, at some sort of regular cadence, I'm going to have a program to process what I've dumped and then produce a result, right? I can get results. So
it's more real time.
Exactly. It's more real time. It's more, you get faster and live, quote unquote, live results versus, more periodic results. And people, in general, I think people nowadays, especially, as technology has advanced, have demanded, I need results now, right? I need results now. I'm going to look at what is going on now versus, oh, this is what happened a day ago, or, 2 days ago, or a couple hours ago. People want results fast. And because of being able to, get the results fast, I'm able to make decisions faster, and I'm able to take advantage of opportunities faster, which leads to, maybe more profit or whatever, other benefit that can arise from that situation. Does that kind of answer your question?
Yeah, it does. Where were the, I feel like you've probably been in the space, maybe not at the very beginning, but maybe for the bulk of this, because I feel like stream processing as a concept has probably existed for a while, but like the data processing needs that everybody has been using to process data, it used to all be batch. And, as you're moving into the stream model, there were probably some scaling challenges, or probably some things that had to be created that didn't exist to handle what types of problems had to be solved in order to make something that would be scalable, robust, ACID compatible, whatever.
Right. Just like you said, stream processing is just like most things, right? Has been around for, quite a long time. There's, papers describing processing, a stream since, probably a couple of decades ago. And there's been, I think, technologies developed, throughout the, last couple of decades around doing some sort of stream processing. But what really kind of the stream processing kind of we're talking about is stream processing in the realm of big data, right? Which that has really, kind of taken off only perhaps in the last, decade or so, last maybe 10 years. So the difference between kind of the more traditional technologies I've kind of mentioned before and what we have now is, look, before there wasn't that much data, right? Thus, because people didn't have so many technologies accessible to them in their daily lives. The level of data generation wasn't that large. So we can perhaps design simpler systems to process less data, even though it could be in a streaming fashion. But as we enter kind of a more digitalized age and people start to generate more data, that's where we get into big data, right? That we have to develop systems that can process orders of magnitudes larger data than what existed before. And it started with batch processing and then it basically got into stream processing.
Okay.
So that's a little bit about.
Yeah, that's perfect. I'd like to get into some specifics in terms of like some of the projects in the industry. And I know you've worked with a lot of them. The Apache project, or the kind of the overall organization, I feel like they do everything. Yeah, but sometimes I look at the list of projects, it's like they do 3 to 10 of everything, and it's some of them overlap. And I feel like you've touched several of these in this space. Can you help me kind of unravel, like, Flink and Pulsar and Heron? Like, there's 10 different data processing solutions from the Apache banner.
Yeah, so there are quite a few overlapping projects in the Apache Software Foundation, but I don't think it's necessarily a bad thing. There's always a benefit for having a little bit of healthy competition. And the thing is, the reality is not all, even though some of these projects have overlapping features, they have their own kind of distinct features that make them kind of successful. So I originally, one of the I think the big projects in the beginning for stream processing in the big data realm was a Apache project called Apache Storm. That's the project I originally kind of worked on and implemented my research on at Yahoo. So Storm was kind of the first generation of big data stream processing platform that allowed users to basically process large amounts of data in a stream fashion and a massively parallel kind of environment. Afterwards came stream processing systems such as there was SAMZA, there was Flink, and there was also Apache Heron that we also worked on at Streamlio, which came out of Twitter as their kind of, they branded it as a Storm 2.0, a newer version of Storm with some, improved features. So all of these kind of have their own unique capabilities from a feature perspective. I think they all kind of trace more or less maybe their lineage back to Storm as one of the more foundational projects that really gained popularity in industry for stream processing and really kind of led the way for stream processing and community. I think another monumental project is Apache Flink, which we also use today in SBS, the stream processing service at Splunk. Flink made some, I think, very innovative features, created some really innovative features around how to reason about time and how to reason about basically when events or when data is generated and how to basically process the data relative to the time that it's generated. So there was a lot of features and work around that kind of around that functionality that really led, I feel like, for the product Apache Flink to take off as well. So Kyle, you also mentioned projects like Apache Pulsar, right? So I guess I can talk a little bit about, well, what is the difference between kind of Apache Pulsar and Apache Flink, right? Those are not necessarily kind of competing technologies. Those are a little bit in different spaces. I think they, in a lot of technology stacks I see in industry today, they complement each other. Apache Pulsar is a publish subscriber system. You publish messages to the system, and then you can have consumers that read message, out the other side, or you can. Another way to put it is, you can have producers that publish to a channel or what we call a topic in Pulsar, and then you can have basically consumers on the other side read out that data. So there's a lot of use cases that can be served by Apache Pulsar, but one of them, and a very large use case, is typically used as a buffer for stream processing systems. So you would always front your stream processing engine with a message bus like Apache Pulsar that, this is where live data will come in, and this is the buffer that will absorb those spikes, right? That can potentially happen.
Like in case your system's compute can't keep up with the stream?
Right. Yeah, that's it's not necessarily it can't keep up. It can't keep up at a certain moment in time. Right. On average, your stream processing system needs to be provisioned in a way to basically keep up with your average kind of throughput, your average, level of traffic. But, as you would imagine during, regular day cycles. Super Bowl happens, a holiday, maybe in the morning, everybody wakes up and, starts tweeting or whatever, right? Whatever events that can trigger these spikes. And, having a message bus in front of your stream processing system, helps basically absorb these spikes so that it doesn't, put undue stress on your stream processing engine. So that's kind of
as an assistant queue.
Yeah. So is it the job of the developer then, and at what point would you make a decision about, okay, what is the state of the queue? We have a lot of latency because of a spike, for example, and now we're we can't keep up. We're 10 minutes behind of this system that has typically less than a second latency, that kind of thing. Where does that decision happen, and what does a developer have to think about there?
And by the way, can our first album, when we form our musical group, be named State of the Queue?
Every episode, Jerry. This is
nice.
Nice. I like that one actually. That's a good one.
Thank you. Yeah. I'll add it to the stack.
To answer your question, how so in a situation where let me first make sure I understand your question, right? So you're basically asking in a situation where the user is seeing higher than normal latency for their results. Is that correct? Like basically instead of a 1 second kind of expected latency, they're somehow seeing a 10-second latency right before getting some results. Yeah. How can us as engineers or whoever is basically responsible for these systems like determine or debug the underlying problem? So there are,
I can pick a concrete example if it would help it might help the listeners.
Sure, why not?
Off the top of my head, we have a stream of alerts. Okay, they're coming from a variety of IT systems, and these are they could be state changes, they could be alerts, and these are coming from hundreds of endpoints, hundreds of thousands of endpoints, and maybe there's a monitoring system that was built around this, and the monitoring system, in order to have there's probably a computer that's going to do something with that alert to understand if this is important or not. And then if it's important, there's going to be a human on the other end to do something about it, perhaps, or not. Maybe there's some runbook automation. And all of this works until it doesn't work. And if everything breaks at the same time, then the whole system is going to strain because of the latency that's introduced. So how do you combat that? What are some challenges, or what do you do in that kind of situation?
So it's interesting that you brought up a monitoring system, because for a lot of these kind of I would classify them as not hard failures, but like soft failures, right? Like not just your system just flops over and nothing gets through. It's more of a degradation in performance, right? A soft failure. So what really needs to happen in these situations is you have to have very good monitoring. You have to have very good tools to tell you that these basically non-hard failures are actually happening. So typically what would happen is you would define maybe some sort of SLA, right? For your data processing. How long I expect the data to flow through the system. Maybe in this case would be 1 second, right? And if my data, periodically, if my data starts missing that SLA, then someone, one of the engineers responsible for the system should basically start looking into kind of, well, why are we missing that SLA, right? So the first thing is to basically define, the SLA, the surface level agreement of what, is the expected latency, and then have the necessary monitoring tools in place to basically alert, developers or, engineers that, we are missing basically our service level agreement, and someone should go investigate to see what happened. But before all of this, I want to say, like, if you in the beginning, before we even have any of this in place, like, you really need to also calculate and provision correctly, right, your system to handle the load that you are expecting it to be. What I mean is, look, if you calculate, right, determine that, look, I will have an average, say, throughput or the amount of data I need to process is 1 gigabyte a second, right? You need to do the correct calculations, and you need to do the correct math to basically configure and provision, the message bus and the stream processing engine to be able to handle that load, and then probably also have some room for have some padding room so that we can absorb some higher levels of traffic at times. So in the beginning, this pre-calculation and this provisioning process needs to be done in a meticulous fashion to make sure that you will basically be able to handle the expected amount of load within the certain amount of latency. So that homework definitely needs to be done. And afterwards, obviously, it's always a best an educated guess at the beginning before you actually run through the load, right? So that's where the monitoring comes into place, where you have to have good graphs and good metrics that are emitted from basically different parts of these, systems, message bus, as well as, stream processing engines, for you to really, be able to have observability into what is going on into those systems and why certain things are taking longer than usual.
So
I always, when sizing things, I always love leaning into percentiles. Mm-hmm. So, for example, like when I would be working with customers to size like their Splunk deployments, I would say, just to be very conservative, I'd say, okay, well, let's pick something like the 95th percentile. So maybe in 100 days, you might go above that 5 times, but that's so anomalous that you should be fine. And so now, like you had said, like, you're not just going for the average, because the average doesn't, like, if you say the average plus some buffer, well, at what type of distribution from the average do we need that buffer to be to handle, 90% of our work, 95% of our work? And that was, I think, when playing with percentiles finally rang true to me. And I was like, oh, now I understand the purpose of a percentile.
Yeah, that's a very good point, Birch, and that's often what we use in the stream processing world as well. In terms of, especially, one of the more critical things that we're concerned about in stream processing is latency, right? Is we want to be able to process things fast, and we usually kind of quantify or qualify how well a stream system is doing by its basically percentile latency. So when we say maybe we expect a 1 second latency for our requests, for our data, what you really kind of want is not necessarily an average latency, because that could then be all over the place, right? Mm-hmm. One could be, one latency could be, 10 seconds, and the other could be 0.1, and you average something out to be 1 second, but in the sense, like, you get very high and very low. So it's that's not a good situation. What you really want is exactly what you said, is percentile latency. So a lot of, when we benchmark stream processing engines and other stream processing platforms, it's 99th percentile latency, right? Which means, 99% of the requests, or 99.9% of the requests, whichever, depends on how rigorous you want it to be, has to be within a certain amount of latency, right? So to be more specific, like, you would typically define an SLA for stream processing as in, okay, that is within kind of the 99.9%, percentile latency. And that number would be like, chosen for basically almost 99.9% of the time, my latency needs to be below that. And that's basically my, the tolerance, right, for my stream processing system.
Hal, what were you going to ask? We have some latency on your question here.
So no, this went in a great direction. So I'm glad you kind of expanded on that.
We need to say latency one more time to make sure this is still technical.
No, I'm not going to say latency one more time. We already said it enough times.
You just did.
So I don't remember what I was going to say next now. Thank you very much. No. So PubSub, I wanted to talk a little bit more about PubSub, and I wanted to know, and I was actually like familiar with PubSub way back in the day. I don't know if you've ever heard of XMPP, the messenger protocol that was it XML markup pub? I forget what it stands for, but even though I was on the standards body for this protocol, but anyway, so I've been familiar with and around that space for a while. I'm kind of curious as to what are the kind of the challenges being solved today. You know, how is the, and I'm thinking it's probably around scale. I mean, and what do people need to understand that is happening in this? Because I think you know. AMQP, MQTT, you know, there's a lot of these types of protocols. It's not new. You know, every cloud service provider has a service. You know, isn't this just taken care of for you? Or, you know, like I imagine this is actually quite a hard problem. And I want to understand kind of like, you know, what are those challenges like?
Yes. So to basically design and implement a system like Apache Pulsar is very challenging. But we offer what is, you know, good about a system like Apache Pulsar or any good, you know, kind of message bus system is you should provide a, you know, relatively easy to use interface, right? It should be easy for the, you know, the user of the platform to use, you know, the system, right? And to basically be very intuitive about the semantics and results of the APIs they use when they interact with the system. So that should be, you know, very easy. But there are many challenges in basically designing kind of a modern, you know, message bus platform today. And what really kind of separates, you know, what we have today versus what people had, you know, say like 10, 20 years ago, right? Message buses have been around for a while, you know, in many different kind of areas, but they tend to be kind of a single tenant, single node, not very distributed. And you really have a very large, a very low cap on the amount of, you know, data that can go through, you know, that type of system. So the challenges really arise when we basically reach a situation where there's just a ton of data in the area of big data, right? There's just a ton of data, and how we basically are able to, you know, process and serve, how we're able to serve that data, that massive amount of data to wherever it needs to go. So let me talk about some specific challenges in Pulsar, right? One is definitely the scale, right? It should be able to handle massive scale, and it should be able to scale very easily. What I mean by that is not necessarily just saying, oh, I'm going to throw more, you know, CPU or memory into a specific node, into a specific machine by just increasing the raw, you know, compute power of a machine. Is I should be able to add just more machines into the cluster, and I will be able to get higher overall throughput. So no longer we're in kind of the realm of scaling up. We are in the realm of distributed systems where we really are focused on scaling out. Mm-hmm. So while that is kind of a cool concept, we have to deal with all of the problems that arises with now basically scaling out and independent kind of, you know, entities or machines working with each other, right? And a lot of that has to deal with, you know, fault tolerance and reliability. In case of, you know, what if one of the machines goes down, you know, or there's a network partition, how do we zone? Exactly. How do we basically still keep the user's data safe? You know, what are our guarantees, right? And what are the trade-offs we are willing to make to basically trade off, you know, durability, you know, availability, and so on and so on and so forth. So a lot of, you know, the complicated problems arises, especially with is fault tolerance, right? It's no longer, you know, we're also building a system that needs to be, you know, fault tolerant and more or less highly available, so that we don't incur downtime on our end users. So we have to carefully implement, you know, all the corner cases and all of the faulty scenarios that could happen, so that we don't accidentally just, you know, drop users' data or something like that.
Okay, gotcha. So, and you mentioned Splunk Stream Processor Service a minute ago. Tell me, you know, a little bit about the impact you might have had on some of our stream processing products.
Yeah, sure. So to give a little background, like you mentioned, I was part of a startup called Streamlio, right? And we were working on a similar technology as SPS or DSP, as we know it back in the day, the data stream processor. We were working on our own next generation stream processing system based on Apache Pulsar and so on and so forth. And then we got kind of acquired by Splunk. So one of the first things,
not kind of. Sorry, we got acquired. There's no one foot out of the door. We became part of the Splunk family.
We became thoroughly part of the Splunk family.
Correct. I find myself doing that too all the time. I'm like very wishy-washy about things that are very clear facts.
Correct. So one of the first things we did was look, like, how can we introduce Apache Pulsar to Splunk, right? We were very adamant about this new technology. We knew this was the next generation technology in the pub sub space, and we wanted Splunk to be able to leverage the full range of capabilities and benefits of Apache Pulsar. So we did some POCs and benchmarks with the existing technologies that were used in SPS, more namely Apache Kafka, Kinesis, SQS, and so on and so forth. The due diligence we did and the benchmarking we did clearly showed, a clear advantage of Apache Pulsar in numerous regards in terms of COGS and, operation costs, as well as performance and latency. And Pulsar, did much better. So one of the first things I led was actually, let's standardize on Apache Pulsar at Splunk for our pub sub. So especially in SPS at that point. So I went in and we ripped out, all of these, I would say, competing technologies, or I'm a little biased, so I'll say, legacy technologies, because they're not as good, in my opinion, as Apache Pulsar. So we ripped out all these legacy technologies such as Kafka, Kinesis and SQS, and we replaced all of, those platforms with just by using Pulsar. And it gave many, advantages, just not in terms of, what the benefits Apache Pulsar offered over those individual legacy platforms I mentioned, but also just look like it makes deployment easy, because before,
was that like a year ago? Like timeline?
That was about a year and a half ago.
Okay.
Yeah. Because in the cloud, we were leveraging Kinesis, and on-prem, our deployments were leveraging Apache Kafka. So there's like two different platforms, pub sub platforms we were leveraging based on different environments. But now we can consolidate all of that to just use Apache Pulsar. And you would imagine, we would have to write, less code, we would have to do less work for maintenance and deployment. And we can simplify a lot of our deployment, because now we've converged on a single platform versus using different platforms, different technologies, and different environments.
Nice.
So I'm sure it would make sense to go into numbers of systems, but maybe percentage wise, was there a certain, percentage, increase in efficiency or reduction in cost that would make sense to share?
Yes, we actually, the head of kind of our group messaging as a service at Splunk, Karthik Ramasamy, has actually given quite a few presentations on the subject of our basically benchmarking of Apache Kafka versus Apache Pulsar talks. And I think not only within Splunk, but also to kind of the broader audience and industry. It's been a while. I don't recall the exact numbers. I would have to go check those slides. But it was
to know that maybe we'll find a way to stick that in some show notes, a link to that talk.
Definitely. I can probably send you some slides, or even send you some recordings on YouTube, right? That has them giving the talk on basically that subject. But in terms of, so we did pretty comprehensive, not just in terms of.
I saw him talk at, it was not at one of our shows. It was like DockerCon like 5 years ago or something. I think you might have actually been there with me. I don't remember. Did you go to DockerCon? No, it was another company. But I want to say that I remember I saw somebody named Karthik, and then later on he came to join Splunk, and it was kind of a funny turn of events.
Yeah, but I can tell you that our benchmark was pretty comprehensive. We did not just compare just raw kind of performance numbers in terms of throughput and latency. We compared also, costs and, not only infrastructure costs, but also management costs. And Apache Pulsar was, in terms of actually running on Splunk infrastructure, was a lot more, better performant and more cost effective than, of course, those two things are, related to each other, but both based on.
So you're saying it was all a numbers thing. You definitely had no emotional bias in this.
Of course, our team definitely had some emotional bias, but we have to, there's definitely skeptical, people at Splunk, right? You always have to kind of, have data to back up, decisions made. So we definitely understood that. So we really wanted to, come up with, as impartial, benchmarking and more and comprehensive benchmarking as we can to just show like, the architects, other, engineering leaders, look, this is a decision that clearly makes sense, right? For us to migrate from these platforms onto Apache Pulsar.
Okay, so and I want to talk a little bit meta about Pulsar and about open source and about what you're doing at Splunk, because and what you did at Streamlio before. Splunk is a commercial software company. We make software, we sell services, but
hey, we make it the software and t-shirts.
The software. But you're working on an open source project. How does that work?
So actually, there has been initiatives within Splunk to really be more active and open source. So, what we do on an SBS as in, also in the messaging as a service team is we, work closely with the community, right? We realize, the benefits of open source community. Like the simple, benefit is that, okay, like we contribute to, the community. The community also contributes back to us, right? They help fix bugs, help implement features that might be, useful for us. And we also, leverage community as a way to, advertise, SBS and products at Splunk, right? Look, there's, quite a few employees at Splunk that are very active in the stream processing space, and Apache Pulsar, they must be really knowing what they're doing, right? They can attract, first of all, the talent to come work at Splunk on this subject, as well as they're significantly contributing and moving the needle. You really want to be in a position to be thought of as a thought leader, right? To be forward thinking as a leader in the area, so that people are like, oh, Splunk is really invested in stream processing. They are active and in the industry, and most notably and clearly in open source. So, it attracts kind of users and people to really, look into and potentially use technologies, such as SBS. And this is not just done for Apache Pulsar. We also contribute to Apache Flink and also other open source projects such as Apache Bookkeeper, which Apache Pulsar uses as its storage layer. So we contribute to, a lot of open source projects. We're actively, involved in, Apache open source community. It's, a good way to, get advertisement for Splunk, but also allow Splunk to access a really, large and good pool of potential future employees, right? This is where you can meet and attract good engineers to come work at Splunk and, further better your product. So there's a lot of, I think, beneficial, win-win relationships between, Splunk and, interacting with the, open source community. Again, like, we're not, leaking Splunk proprietary technology out in open source, just to be clear, like there's definitely secret sauce, right? That we're keeping in-house, and that's what makes Splunk valuable, right? There's
it's
lots of
ketchup
secret
and
sauce.
mayonnaise.
Exactly. but for these, technologies that, are more generic and complex, we would like to kind of leverage, the community and people working at other companies to really kind of develop these fundamental, right, infrastructure level projects, so that we're not just on this, we're not taking on this humongous or Herculean effort ourselves to basically develop these projects. Like I said, these things are super complex, right?
Yeah.
Are super complex. They require a significant level of experience to operate. So with the community, we get a lot of help. So, like anybody, like we're not in this, scary journey ourselves, right? There's other people in the journey with us, and it really kind of, helps makes these fundamental or infrastructure level, products better, at service or platforms better at Splunk.
So you work on our like our SPS, our data stream processing product from the engineering side, both in the, now are you working on it from the cloud side as well as customers that deploy it on premise, or are you focused on one area?
Yeah, so I've worked on both sides, but nowadays we tend to shift our focus more onto the cloud offering, as that's kind of a company-wide initiative, is to be more cloud focused. But yes, we do have an on-prem version of SPS. It's still called the previous name DSP, a distributed stream processor. So I have worked on basically helping solve issues and, developing the product on that side as well. And then
go ahead, Hal.
I was going to go back to Pulsar for a second, because you're credited with creating some Pulsar features, like Pulsar functions, IO, and there's a SQL interface. I was kind of curious, are those things that you're able to develop, while you're here at Splunk, or are those things that were mature by the time you came to Splunk?
Like as part of your job function?
Yeah.
Good question. So we definitely want to leverage open source as much as we can, right? The existing functionality as much as we can. But we inevitably run into situations where, what is there in open source maybe meets, 90% or, 80% or whatever measure of what we actually want to do at Splunk. So, we need to basically take that feature in open source, that extra 10 or 20% of the way, to basically really get it to work to meet the needs of Splunk, right? So that's definitely, one of those things that has happened during my tenure here. So one of the additional things we use in Apache Pulsar, we leverage is, Apache Pulsar IO, which is a connectors framework that's also built on top of the Pulsar functions framework. So we're basically leveraging that framework to ingress and egress data in and out of basically SPS. So there are certain features that we had to implement within that framework, or have to contribute to open source in that framework to basically, get it to work in the way that we wanted to work at Splunk, right? One of the features we contributed is a new kind of runtime called the batch source, right? Versus traditionally in Pulsar IO, all of our
batch in stream.
Well, it's a little, perhaps it's not the best name, but it's basically a source that goes out and reads things in a more of a periodic fashion, reads out, tries to basically ingress data that's more static versus in a stream fashion kind of sense. So originally the Pulsar IO framework was designed to just basically read, streams of data and ingest it into Pulsar. But at Splunk, there are, various constraints and various use cases that, we want to do this in a more periodic and batch fashion. So one of the use cases is, say reading from an object store like S3, right? Or, reading from a large file. You typically don't want to, you don't want to just be constantly pulling the file for, new data or whatnot, in more of the streaming sense. You kind of want to just periodically check, right? To say, and that's good enough to say, okay, like, do I have more data in the file, or do I have more files I want to ingest, and so on and so forth. So, we've definitely, there's definitely a lot of use cases that...
I want to stop you. I want to geek out on that one particular part, because I can relate this to what Splunk admins and, are probably familiar with, which is the evolution of our AWS, add-on and the ability
push
to
versus
pull data. Yeah, so you got push versus polling. You could take an S3 object, you could watch it with SQS and have that let you know that you need to go pull. You could send it over Kinesis, Firehose. There's a bunch of different options. What is Pulsar doing better or different than those previous options?
So basically, that's a good question. What a lot of the is offered by, the Pulsar functions framework and, indirectly by the Pulsar IO framework that's based on Pulsar functions is it allows the user to really focus on writing the business logic, the logic to actually just go fetch the data. Mm-hmm. So the framework itself handles a lot of the things such as state management, right? Periodically, you might want to, checkpoint where you've read to, how much you've read. So it gives you, a fault tolerant, performant, stateful interface for you to basically checkpoint anything or store any state that you might need. Also, what it provides is, fault tolerance, manageability and scale. Like, let me go one by one. Like in terms of fault tolerance, like the platform is in charge of how to run and where to run, your business, your code to fetch the data. It's not up, the user, the developer, the connector developer does not need to figure out these details, these operational details about how to execute their code. The framework will do that in a reliable fashion for them. Also, in terms of scale, there are basically tools that can be easily used to scale the number of to scale your rate of ingest or your rate of egress by simply running more instances of a connector and so on and so forth. So you can easily call out to some sort of API and say, oh, instead of running one instance, I can run many instances of that. And the framework will be in charge, will take care of the scheduling and running and all those other things I've mentioned to basically, execute that code in a very parallel and reliable fashion. Okay.
No, that makes sense. I remember trying to build a system like this out of baling wire and tape, it might have been at the time, at previous employer where it was a retail establishment and they had 2,500 stores, and we didn't need to do something once. We had to do something, 2,400 times, something. And that was often, for example, polling systems for, health metrics, having to have that complete within 5-second time frame because that was the protocol constraints. And we had to multiply that out. You can't do that with a single system. So I totally understand kind of the challenges of that. It sounds like the space has come a long way since I was involved in that. So I'm really kind of excited to hear about whether that's, evolved over time. As we kind of, look to wrap up here, what's coming in the future? What things excite you about this space generally, either PubSub or, Flink, Pulsar, or Abstract?
Without revealing anything, we're not allowed to reveal about our roadmap.
Yeah, but he can talk about his open source hat on.
Yeah, exactly.
Yeah, man. Talking open source.
Yeah, there's definitely, a lot of, interesting features that we're looking to implement in Apache Pulsar, relating, around kind of auto sharding, topics and so on and so forth.
define sharding for a second.
Auto partitioning, maybe that's a better way. So, one of the ways to say, to scale out your throughput is to, one of the typical techniques, in big data systems is to shard your data, right? Instead of writing everything into one shard or one partition, you write it into multiple independent shards so that you can basically scale your throughput. So currently in Pulsar, that's a static number someone determines right beforehand how many partitions or shards I want. But in the future, we would like to basically have some sort of feature that automatically determines that based on your throughput, right? Say your throughput at the beginning is 10 megabytes a second. One shard is good enough. In the future, it goes up somehow to 100. It will automatically basically shard your data in a way that we can keep up with basically that throughput so that the user does not need to manually tweak how many shards that, that is needed to sustain a certain amount of throughput. So there's a lot of challenges and features like that, especially when we talk about how to, auto shard as well as maintain, ordering when that happens, right? When you create more partitions, you still want to maintain the process ordering and so on and so forth. So there's a lot of challenges in that. And just in, what I'm also excited on is, at Splunk, we operate certain technologies we basically support some use cases that have tremendous scale. I don't want to, reveal any particular customer or anything like that, but
tens of megabytes.
Yes, in 1940. Yes. That'd be a big deal.
They used two floppy disks.
The last time I heard a specific number from Splunk announced publicly, I want to say it was on. I want to say that Doug Merritt or Sender or Tim at some point had said that we processed, on the order of petabytes a day for some of our largest customers. That's probably the last specific number I recall. I don't know if you remember anything differently, guys.
Yep, that's basically we do have use cases are in that range as well. And for stream processing, that's really record breaking. To be honest, I've worked at many different places, interact with many different engineers that are at different places. That level of throughput and data we can handle is record breaking for not only Apache Pulsar but also for Spark. Like, we're definitely pushing the limits here of what is possible with stream processing, and we have developed a lot of, I would say, ingenious and clever ways to get around some of the scaling problems we have faced to basically satisfy this large, these large throughput demands of some of the, customers we interact with. So it's definitely, what excites me is because we have these use cases, we can, we are able to think about clever ways and really push, the technology forward, right, to be more scalable and more performant. So that's definitely, what really excites me to, work on these things at Splunk.
Awesome. Well, Jerry, I just have one more question, and I want to know, what commission do you get every time someone forks Pulsar on GitHub?
There's a secret society in which I get no option. Perhaps just a theoretical or conceptual pat on the back, and maybe a thumbs plus from from somebody, but just a satisfaction. Look, that I was with Pulsar from from very early on when it was open sourced at Yahoo, and even when it was closed sourced at Yahoo, I interacted with it in a limited sense. But just to see the project grow from just being started from one company to being used by so many different people, it is tremendous, right? The journey we've come, and just the satisfaction of I wrote some code, and now it's useful to, a bunch of people, hopefully, making society and, humanity better. Who knows, but who knows, right? But hopefully, let's just say they are doing that, and it's for the benefit of society in general. It's just, a satisfying, feeling, right? There's, not necessarily any sort of financial, gains, but just, that I've made a difference. You feel like you've contributed, you've contributed something useful, to industry and society.
That's the reward, right? Is knowing that every time someone forks, you've made the world just one shard better.
Hopefully.
Hopefully. Well, Hal, I feel very Pulsared. I feel very content here. Any final thoughts on your side?
Yeah, go like the project on GitHub. We need more stars.
There we go. Because there you go. It really is. Yeah, that's like you just patted Jerry on the back. All right. Yeah. Thanks so much, Jerry, for coming to spend some time with us. Super fascinating topic, and best of luck with it.
Thank you very much. And thank you guys for having me on today. It's been a pleasure.
And to all our fans out there, stay tuned for our next episode. Like James Bond, we will return. And with that, happy Splunking.